Hello everyone, it's September 30th. Alright, let's do this. Oh, easy question, which means we can... we actually did this one yesterday. Yes, we did this one yesterday, so we can actually progress to the next one. Alright, let's go water bottle. There are num bottles of water bottles that are initially full of water. You can exchange empty water bottles from the market with one full water bottle. The operation of drinking a full water bottle turns it into an empty bottle. Given the two integers, return the maximum number of water bottles you can drink. So I have none water bottles so basically this is the exchange rate, right? So you have 9, so definitely you can drink all 9, and then exchange rate is 3, so you can drink 9, and then there are 3, so we got 3 more. Then we'll add up to this, then 3 will get 1 more, then we add up to this, so in total it will be 13. Yeah, 15 is the same. So 15, basically I do 15 and I divide by 4, which is 3, right? Which is 3, 3 with remainder is 3. So 3 plus 3 is 6. So 6 divided by 4, so we got 1 with 2. Right, now that's it. We can do no more. So yeah, that's only... So we got 15. Hold a second. Hold a second. I think it'll be easier in this category. We do 15. Divided by 4. This one we get is 3. Remainder is 3. So in that case, basically, we're saying we will drink 12, right? We drink 12, and 12's been taken, and then we have 12 has been drank. We have drinking 12. Now we have 6 left. We have 6 full bottles left, right? And now we do 6 divided by 4, which gives 1 or 2. So this one we drink 4. Then we have 2 left, but we don't have... we have 3 left, but we don't have anything more, so we just plus 3. So this is like if the sum of this you cannot, it's smaller than num exchange. So this gives you 19. I think this is an easier way to see this. Easier for me to see. Oh, we're gonna make a new. Another month. One, 5, 1, 8. Alright, so what we have is int rest equal to 0. And what we need is quotient is num bottles divided by num exchange. Remainder maybe I can use a do what? Wow. Do this while q plus r is larger or equal to num exchange. How is it not defined? Oh, I cannot do that. Alright, then. Oh, I need to. I see. Something like this, right? And then rest will plus equal to q times num exchange. And then, ooh, num bottles, that's fine, we'll change num bottles. So num bottles will equal to q plus r. Oh, num bottles. Num bottles. While num bottles is logical to num exchange, then we'll do this, right? We'll do this, and then we'll do this, and then I'll return rest plus num bottles. I feel like I don't know, maybe there is an easier way, but shall do. So when did we do this last time? 2024. Okay, that's about it. And we'll terminate this. And this is a triangular. Let's go here, go to contest. Do I do this? Oh, okay. Split array with minimum difference. Give an integer array nums. Wait, hold a second. I think I didn't do the other one either. Biweekly. I did this one. How about the next one? Oh, I did this one as well. Oh no, this is the one that. Oh, I did this one. But I don't think this is a very good solution. Oh well. You wanna try this? Yeah, let's give this a shot. Given integer array nums of length n and integer k, you must select exactly k distinct non-empty subarrays. K distinct non-empty subarrays. Subarrays may overlap, but the exact same subarray cannot be chosen more than once. A value of a subarray is defined as max minus min, the total value of the sum of the values of all chosen subarrays. Return the maximum possible total value you can achieve. So we'll choose K. I think the other question is you can overlap. So it becomes very simple. You just get a max and get a min, and then we're done. But this one says you cannot overlap. Not overlap. You cannot have the exact same. You can still overlap, but you cannot be exactly the same. So in that case, 1, 3, 2. We can still do. So what we want is the maximum possible total value. So each subarray we need to, so k equal to 2, so I need 2 subarrays. Right? So 2 subarrays. The first one can be this, the second one can be this, and then we got the same thing. And then 4, 2, 5, 1. So I notice 5 and 1 is here, so we definitely take one of this, and I'll take, so this will be 12, right? So basically, we find the smallest and we find the biggest, and then we try to take as many as we can, right? Because the smallest will have the min at a certain position, we have the max at a certain position, so this is the minimum subarray that give us the max possible value. And then we'll do extend to the left. Once we're done, we extend to the right. Well, I mean, actually no. So we have however many we can say. We have x on the left, we have y on the right. So the total number of subarrays that contains this is actually, y plus 1 is x plus 1 times y plus 1, right? So in this case, x is 2, so it's 3 times this is 1, so we have 3, which is a match. So we do this, right? If it matches, if it's larger or equal to k, then yeah, we can take however many we want. Now if it's smaller than k, right? If it's smaller than k, that means we need to find secondary. So I need to keep, so secondary, we want the max, so it will be the max. So we do the same thing, the max will do the second min, right? Secondary min. So we start with the max and the min, and the next one will be max and the secondary min, and then we do the same thing, and we keep doing this until, but keep this in mind. If we do the secondary, they might overlap with the previous. Ooh, yeah, we might overlap though. No, we will not overlap unless the secondary min, like if the secondary min is here, right? Secondary min is here, then we will overlap. When we hit the min, then we will overlap, right? And also if the secondary min is here, right? If the secondary min is here, then we'll always overlap. So in this case, the secondary min doesn't work. Ooh. Okay, so now what we're talking about is we want to find the max position. Okay, so we know the max position, and the rest can be anywhere. So we want to find the minimum. Yeah, let's say minimum is here, right? Let's say minimum is here, and then we can do whatever we want. And then the secondary minimum It depends on where it is located based on this, right? So if the second minimum located here, then we cannot do anything because the minimum is actually become minimum, right? So secondary minimum, if it's here, right, it's the secondary minimum is here, then we can do all the way until we hit the minimum, until we hit this. So we cannot go beyond this, right? Yeah, we cannot go beyond this, which is actually not an issue of overlapping. It's an issue we cannot include this, right? We just cannot include this. Anything that does not include this is fine. And if it's on here, it's the same, and we just cannot include this. And then once this is done, if it's not enough, then we need to have a third minimum, right? Again, a third minimum cannot be anywhere. So from max to third minimum, it cannot include the first two. So if the second minimum is here, then the third minimum. So now is the question. We are exhausting all of them, right? Like in here, third minimum. Yeah, I think it makes sense. Because if you don't take the second minimum, if you don't take the minimum, they say, I'll take the second minimum, and then it can give me more, and then you're not doing it right. Yeah, so I think this is the right way. It's just, so basically, right, we have the position of the max, and we have the position of, let's say we have max is at position I am, right? And then we have minimum position, we can say J0, and then we do whatever we want. And then we have the second minimum at position J1. So is there a systematic way to the minimum? Well, we'll check. All right, we'll check if J0 is in between. And if J0 is in between, then we basically cannot do anything. But if J0 is not in between, then we can, right? J0 is not in between, then we can do, but then you have to analyze if J, and the thing is, once we get a few of them, right? So we have like let's say a JN comes in. I have all the previous positions, right? We have all the previous positions. Now we get a new one coming in. Again, as long as one of them is in between, then we cannot do, right? We cannot do. That begs a question of how do we find out? Well, what we want to do is to keep. We want to keep the minimum that's closest to the maximum, right? Then we know if a new comes in, it's kind of outside, then we cannot do anything. It has to be, the new one has to be more to the inside, right? It has to be more to the inside. It has to be somewhere that the previous one doesn't exist. Okay, yeah, that's fine. That's fine. It's totally fine. And oh yeah, I think it's doable. I think it's doable. We have the maximum here, right? Maximum is here, and then we have the closest on the left hand side, right? So we can say I left, and I have I right. Initially, I left will be -1. I right will be, the total length. I right will be n. So anything will be, within, right? Anything will be within. So every time we do this, we get it smaller. We get it smaller. We get it smaller until we cannot find any more, which I think it's guaranteed, right? It's guaranteed I can get k. Yeah, we can always get k. Yeah, we just kind of shrink, and then we have the limit, and then I think we can do this. All right, or write one very fast and then see if it works. If it does not work, then yeah, it just does not work. We'll figure something else. Ooh, what the hell? I did not intend to code this in Python though. Find the index of the sort nums and attach its index and attach the index of each number with it. The index of the max value is the anchor. Right. Each time we use the currently unused smallest value. If this value's index lies within the boundaries formed by previously used smallest values. There will be no overlap with the previously used smallest values, and we can form new subarrays as long as they do not go beyond the boundary. Otherwise, the current smallest value cannot be used. Right, we continue doing this until k is reached. We need to sort, so it's O n log n. Alright, so first things we need is a vector of pair int it's num indices I0 smaller than nums.size I plus num indices dot pushback nums I sort num indices begin and okay, so now int anchor is num indices dot back dot second. Right, that's the anchor. Left bound -1. Right bound is nums.size. Yeah, nums.size. Okay, so I have these two. And then we'll go int long res equal to 0. And we'll have also int. We can just do k, which is fine. For int I equal to 0, I smaller than nums.size -1 plus. So for each one, int j int val is num indices I dot first, j is num indices I dot second. If j is larger than this and j is smaller than right bound, okay, then we can compute the total number subarrays. Sub count shall equal 2. So I have j and I have that. So basically, but we want to know if j is on which side, right? We don't know which j is on which side. So if j is smaller than, then we do this part. If j is larger than, okay, so in count is 0, right? If j is smaller than anchor, we'll do something, else we'll do something. So if j is smaller than anchor, then it's going to be the total number from j to the anchor, but j to the left bound. The left bound cannot be taken, right? So it's going to be j subcount shall equal 2, right? J minus left bound multiplied by right bound minus anchor, right? Right bound minus anchor. Else, maybe I can do it like this. J is smaller than anchor, right? If it is true, then we do this. Otherwise, wait, hold on. Question mark. Otherwise, j is larger than the anchor, so it should be anchor minus left bound times right bound minus j. So that's the count, right? If subcount is larger equal to k, okay, subcount is larger equal to k, then we all just do k of them and then we terminate. So rest or plus equal to static cast long k. Actually, we should do k remaining equal to k. Okay, then we don't need to static cast because remaining will be multiplied by nums anchor minus nums j. Oh, I have value minus val. Rest will do that and I'll break, right? Else rest of plus equal to remaining, not remaining, subcount times nums anchor minus val, and then remaining or minus equal to subcount. Then we'll continue. Oh wait, hold a second. We have one more thing to do, which is actually I think it does not matter. This is within, then we definitely need to update it. But if it's not within, then we don't have to. Yeah, if it's not within, we don't have to. So again, if j is smaller than anchor, no, not j is smaller than, if j is smaller than anchor, right? J is not anchor, then, whoopsie doozy, we should say left bound should equal to J. Else, right bound equal to J, right? Right bound is J if J is larger than anchor and is smaller than right bound. So yeah, we'll keep doing this until we get out, and we will return res. Alright, we'll give this a run. If it does not pass, we'll debug it some other time. Looks good so far. Did not work. Huh. We passed 119 test cases, which is pretty good. So, but there's still some issues. We'll deal with the issues. But I feel, I don't know, it feels right to me. Expect 52. Oh, this is I think the full thing. That is an edge case. I did not consider this edge case. Where like, yeah, 1. And then we'll choose this. Oh. Oh, shoot. I think I know. I think they're still remaining. Damn. Remaining. Yeah, I think they're still remaining. That's why my answer is 51 instead of 52. There we go. Yep. Yeah, so just have to run this. Basically, oh lord, we have to rerun and have a new anchor. And we cannot cross. Yeah, we basically have to have a new anchor, and we cannot cross the previous anchor. Damn. Okay.